Thank you very much. I hope that everybody can hear me. First, I want to thank Impeda that invite me to give this presentation. This is a presentation on not only on RAS system, but how you can improve and optimize different systems to produce a better and a more sustainable fish and other organisms. I just want to give a very brief kind of view on the Indian aquaculture. As we heard earlier from different presenters, the Indian aquaculture is booming. Over the last less than 2 decades, it's doubled from 6 million to almost 12 million tons of fish. With shrimp, it is even more impressive. In the last decade, from 100,000 to 700,000, almost. However, in the last 2 years or so, there is kind of a stagnant or even reduction in production. There are different factors for this reason. As we heard earlier, one of them is definitely different pathogens and disease outbreaks that reduce and cause loss of production. With the ornamental fish, they are obviously not near as big as the fish, edible fish and shrimp, but still they are contributing quite a lot to different households, especially since women are the ones that occupied in this industry. There are different aquaculture systems employed in India, like anywhere else. The biggest, obviously, is earthen ponds. They are introducing of plastic-lined ponds, cages, onshore tanks, a different variety of intensity, and agri-aqua, which means, like usually, it's rice paddies with fish or shrimp. This table kind of giving a brief view of the intensity of the different systems. Obviously, those numbers are kind of an average and just a snapshot, not necessarily really to the point. If you look from the left to the right, you can see from extensive ponds that can be from just few hectares to up to 40 hectares. Production usually in India is quite small, 1 to 2 kilograms per cubic meter. Water use is quite high, 5 to 2 cubic meter per kilogram fish produced. And annual yield in India is still quite low, between 10 and 20 metric ton per hectare. There are quite a lot of challenges with the extensive ponds, competition on land. Water resources are getting scarce, especially now in India with the drought. And obviously there is no control whatsoever on pests and pathogens. More intensive systems onshore, either concrete tanks or lined ponds. They are obviously smaller. Their production are higher, 10 to 30 kilograms per cubic meter. Water use usually is lower, 1.5 cubic meter per kilogram fish produced, and with a much higher annual yield. Again, challenges include high water use, construction cost obviously, and energy cost due to the aerators that need to be used. We heard earlier that cages are getting more and more into India. Usually those are smaller cages, not like in Europe or the Mediterranean. They can occupy areas quite large, from 1 hectare to bigger ones. Production load is 30 to 60 kilograms per cubic meter, sometimes lower, depending on the species, obviously. Water per kilogram produced, well, there is no water per kilogram used because they are in a body of water. Annual yield, anything between 3 to 20 kilograms per cubic meter of water. Again, there are quite a lot of challenges there, environmental impact, especially when it's in the area of mangroves, and again, no control on pests and pathogens. Also, algae blooms, red algae blooms and other algae blooms, toxic algae blooms are now getting more and more apparent. Smaller concrete tanks, usually used by ornamental fish industry, production is smaller. Obviously, when we are talking about ornamental fish, it's not per kilogram, it's per fish individual. Water use is relatively low, but usually the water quality is a problem, because in those cases there is a basically static or low flow of water. And then we are moving to the most intensifying system, the RAS, or circulating system. Very small footprint. Production load can be quite high, 60 to 200 kilogram per cubic meter. Water use is very, very low, less than a cubic meter to a kilogram fish produced, and annual yield is very, very, very high. I will talk about the challenges in a minute. So moving into RAS, so circulating system, culture system that reuse the water more than once after some form of treatment. The most fundamental problem with RAS systems is keeping the water quality while removing the waste product in an economical manner. Economics is everything. And the problem with RAS in many, many areas in the world, especially when RAS was just introduced, many RAS operators lost and failed due to the initial high capital and operating cost that was not really calculated and managed correctly. Just to give you an understanding how RAS is getting into Asia, this is from just like a week ago from the IFID link that state that from 80% a year ago, now CP produce 30% of its shrimps in RAS systems. By 2023, CP wants to move completely to RAS system, all the shrimp, all the Thai shrimp that they are producing. So this is quite significantly. What are the advantages in the RAS system? The first is obviously fully control on the environment. There are no temperature changes, algae blooms, rains, flooding, poachers, and many, many other factors caused by the environment. Obviously, low water use, efficient energy use, the footprint is very, very small, high density culture, minimize volume of effluent, you don't need to treat a lot of waste, allows increased control over all the culture environment, and improve, and that's probably the most important thing, improve the biosecurity and disease control. If you manage RAS system correctly, you shouldn't have any disease. Obviously, there are constraints. Not everything is rosy. The most important thing is the high upfront investment in material and system that need to be, to put for a RAS system compared to any other system. High operation costs compared to other aquaculture systems. And very important in India specifically, there is a need for trained staff and to monitor and operate those systems. Those kind of trained staff are still quite lack in India. And obviously, electricity is needed 24/7. It's not like a large earth pond that if you don't have electricity for a while for the aerator, the fish will still survive. In this case, even an hour without electricity, all your crop, all your stock can die. RAS systems are not one size. So it's not like a RAS system that design or build in Norway will suit to India condition. There are many, many different sizes and range of sizes of RAS, from several or even tens of thousands of ton production, mainly nowadays in salmon in Norway and North Europe, to a very, very small aquarium sizes. RAS can be a complete close or almost closed. Usually when you say close, it's never 100% closed systems. It can be 90, 95, but not more than that. Or it can be a very, very simple system that adopt only one or few of the RAS components. It can be designed from the ground up as a turnkey operation, building everything, including the fish tanks, the recirculating system, and everything else. Or it can be retrofit to existing system. The most important thing, it has to be tailored to the needs of and the conditions of the users. Few RAS basics. RAS need to deal with few things. The first thing is removing organic matter by mechanical filtration, removing the toxic ammonia and transfer it into harmless nitrate by a biological filter, removing the CO2 that the fish are basically removed to the environment, and enrich the water with oxygen. And the last thing, obviously, disinfection from the water from any pathogens and bacteria. Just a schematic, this is just a simple schematic way to demonstrate those systems. And I said system can include all or just part of those components. The first thing, as I said, solid removal by mechanical filtration, moving into a biological filter, and then degassing column or trickling filter, sometimes then followed by oxygen enrichment with liquid or gas oxygen, and then you have a UV disinfection or sometimes ozone disinfection. When we are looking at solid removals, there are many ways to remove solids from the water. The most common one is the drum filter, which is basically a drum covered with a mesh that separates the solids from the water, the waste going out, and the water going continue to the system. Then you have a baffle tank that it's very, very simple methods to remove solids. Large tank with several different barriers in between, so the water are moving very, very slowly in it, so the heavy solids sink and the water goes out of it when they are clean. Then you have at the bottom, as you can see, banana screen or parabolic screen when the water is coming from the top of the banana filter and moving through the screen, while the solids, as you can see on the right pictures, I don't know if I have a pointer, don't think so, but on the left side you can see this orange stuff. This is a banana screen from Artemia production site. So the orange one is actually Artemia. Another way to remove solids is Swirl Separator or hydrocyclones. It's a very simple conical tank that the water are coming into it parallel to the wall, create kind of a vortex like what you have in a sink when you open the tap. So the solids concentrate at the bottom. You can see in the red circle at the bottom, the solids concentrate there, and you can remove it out, and the clean water are going on the other side. It's possible to have individual cyclone to each production tank, so most of the heavy solids concentrate that and reduce the load on the system. The next stage is, as I said, the biofiltration. It's a two-step nitrification process by bacteria. Those bacteria turn the ammonia, the harmful ammonia, into harmless nitrate, but those bacteria need a site to sit on. So you need to supply a substrate to the bacteria to attach to so they can do their work and turn the ammonia into a nitrite. Those materials can be almost anything. You have the blue bioballs on the top that are made specifically for this purpose, for biofilters. They're called bioballs. It can be organic gravel on the side, or even oyster shells. You have those tubes that are actually tire recycled materials, or even, you know, Coca-Cola bottles, cups, as you can see on the left side. The degassing process removes the CO2 from the water, reduce the CO2 by exchange a lot of air from an air blower moving through the water. So the exchange of air and water reduce and remove the CO2 from the water and enrich the water with oxygen. What you see is a different ways of basically degassing towers, small and big, that basically move water through air or air through water. What I want to do now is just give you a brief kind of overlook of different systems from different parts of the world. Some of them are very modern and sophisticated, some of them are much less. Just to show you the way that RAS can be incorporated, or parts of the RAS systems can be incorporated. In this case, this is an ornamental fish research station in Singapore, a very sophisticated place, but the system is very, very compact. It's only 1 cubic meter tank at the bottom, the system hole sitting above that. The bottom tank is a reservoir. You have a cartridge filter with UV on the back, with biofilter where you see the bioballs there. A completely different system. This is from Malaysia. This is ornamental fish. I think it was koi, as far as I remember, with individual biofilter tank in each tank. As you can see here, the water are going from the fish tank, from the bottom, going up with a small submersible pump into the biofilter at the top. You can see the water spraying on the right corner, reducing the CO2 in the water and enriching the water with oxygen, moving through a biofilter at the bottom, biofilter media, and then going back into the tank. Again, a different ornamental fish farm with replacement plastic liner. So at the end of each batch, the plastic liner can be removed and replaced without need to wash the tank or disinfect the tank. Biofilters here are quite different. Those are, as you can see in the top photo, you have 2 buckets with kind of a white spaghetti. Those white spaghetti are plastic residues, you can say, or plastic spaghetti from the plastic industry, from molding, and they act as substrate for a biofilter for the bacteria, as I mentioned. You have airlift. You have a small airline with airstone, bubble at the bottom, and push the water up through those plastic spaghetti, and by that, the bacteria accumulate on those plastic spaghetti and do their work and reduce the ammonia in the tank. More or less the same principle here. Here it's like a large tanks, large facility that all the water are going into a central biofilter. If in the previous one it was individual biofilter for each tank, here you have a central system that the water are going through a biofilter. Again, the same plastic spaghetti in those bags that the water are going through it. This is a completely different, you can say, scale of operation. This is a compact RAS. All the components are on skid or pallet. This is from Turkey. In this case, it is a RAS for a marine system, and therefore you have a protein skimmer. This is the tower with the clear tube on the top. Usually in freshwater, you don't need this protein skimmer, and therefore the system will be smaller. The advantage of the system like that, it's more or less plug and play. You are bringing the whole lot in a container, put it in the system or near the tanks, connect the in-water, the waste outflow, and the water flow back into the system, and you're done. You can actually install a system like that within a day. So it's reduced installation cost, obviously, and time. It maximizes efficiency and minimizes the footprint, all in one. Another all-in-one water treatment is slightly different. This is not on a skid, but it incorporates most of the factors in a RAS within a one biofilter reactor. As you can see on the right side, this single-pass biofilter includes particle filtration, CO2 removal, ammonia removal, and water oxygenation. Again, it's very easy to install. You don't need a lot of time or money to install it. It can be used with existing systems. So you don't need to buy the whole system. You can just build the biofilter, or you can build it, as I said, from the ground up as a completely new infrastructure. Low investment. Those systems are relatively cheap. Obviously, relatively, they are still more expensive than earth and pond, obviously, but relatively cheap compared to European system. Again, very small footprint. Low energy consumption is also relatively small. This is a system, I think in Israel, as you can see, there are two systems, one on the right, one on the left. You can see the bioreactor on the left. This is the bioreactor with a small drum filter and a small reservoir behind it, as you can see. This is the bioreactor. It includes the biofilter, trickling filter on the top, and you can see the blower in the middle of the reactor. This is a photo from the top. You can see the trickling filter and the water coming from the top down into the reactor. The same biofilter reactor can be also installed in ponds. In this case, those are intensive ponds, and the bioreactor was installed after the ponds were working for several years. Same situation, but in more intensive concrete ponds. You can see that the installation on the side. And again, it's pump water from the concrete pond, increase it into the water, into the bioreactor, and the water in back. You can see from the orange pipe, those are clean water and increase the quality of the water. Similar system, those are concrete tanks, ornamental fish farm with individual bioreactor in each section. I just wanted to give some numbers just as an example for a very, very small RAS system. In this case, it's a RAS system built of 8 tanks. Each one of them is 10 cubic meter. And it's the maximum annual production is 20 metric ton, so it's very, very small. The footprint is only 350 square meters, so really small footprint. The maximum biomass, as you can see, it's quite high, 80 kilogram per cubic meter. Again, it's a catfish, African catfish. I don't want to go over the water conditions that this system can maintain, but as you can see, the dissolved oxygen that it can maintain is quite high, 7 milligram per liter, which is quite optimal. Just as a comparison, and on the bottom here you can see Pangasius ponds culture in India, averaging between 10 and 15 metric ton per hectare. To remind you, this system, the small system, can have 20 metric ton in 350 square meter. So much, much, much higher. So for summary, RAS, or recirculating system, is relatively new technology in India, and in fact in many, many parts of the world. Increased capital and operation cost can be offset by better control over production and a higher yield, much higher yield. System design and operation does not need to be complicated, and also does not mean that you need to spend tens of thousands of dollars on a system, especially if you incorporate only one or several components of the RAS. If operated correctly, RAS and a system which, as I said, incorporate RAS elements can significantly improve yield and better growth and survival.